In this video, we're going to look at kind of applying what we've learned with systems of particles and velocity and acceleration and impulse and momentum, and kind of put it all together and see how the things we've learned about collisions and explosions and conservation of momentum allow us to apply Newton's laws to new kind of situations. So if you think about a system of particles, right? You've got mass 1, which is got a position vector r1, and mass 2, 3, 4, etc. We could find the position of that system of particles is basically the center of mass of that system of particles. So that little red X represents the center of mass, and therefore the coordinates for the system. And so this is important because we want to be able to switch back and forth between this idea of center of mass and the idea of, well, this is the point that represents the whole system, which is actually what we were doing before we defined center of mass. We sort of always said anything that we're treating as one object that is, in whole has a single point. And that is the position vector for that center of mass. So if we can figure out the position of a group of objects of a system, then it stands to reason that if you take the time derivative of that position, you could find the velocity of the center of mass. And if you did it again, you could find the acceleration of the center of mass. And then that means that if we knew the velocity of each of those particles, we could do a weighted average and get the velocity of the center of mass or the acceleration of the center of mass in that same way. So if we think about the velocity of the center of mass, right, we can think of this as momentum of the system divided by the total mass. Because isn't this top row there, if I grab my pointer, right, m1 v1 plus m2 v2 plus m, and so on and so forth, that's just the momentum of the system. And so if we think about a system, we could think about, well, what's the velocity of the center of mass here? Well, we have a mass going up and a mass going down. And since they're different masses, obviously the distribution of mass in the system will be different at different times. But the momentum of the whole system is just mass 1 v1 plus mass 2 v2 divided by the total mass gives us our velocity of that center of mass. We can find that, and it ends up being negative because the larger mass is moving down, right? The smaller mass is moving up. They're both moving at the same speed. But the big thing here is that the bigger mass, which has more momentum, dominates the situation. Right, so there's the center of mass, and it is moving down. It's closer to mass 2 for obvious reasons. But it's not moving down as fast as mass 2 is because mass 1 is also moving up. What about the acceleration of the center of mass? Well, for this, it's mass 1 times acceleration 1. But what is that? But the net force on an object. So if you sum up all the forces of each object on each object, we can think of that in two ways: the net force on each individual particle, or since we're treating it as a system, we may as well think of it as the sum of all the forces that are inside, which are all going to cancel out because the force of object 1 and object 2, if there is one, is inside the system. And then the net force is external. And so what we end up with is that the acceleration of the center of mass of a system is the net force from the outside divided by the mass. And that goes with that same definition. If there's no net external force on a system, that's when we said momentum of the system was conserved, right? So we can think of this in some interesting ways. If you think of, a hammer, this is an axe. I don't know if you've heard about these places where people go and throw axes for sport. It seems highly dangerous. I'm surprised they can get liability insurance at targets. But if you look at this object, it's a complicated motion. And we looked at that video of the tennis racket being thrown. And if you watch one end of it, it's a complicated, cycloid kind of shape. But if you watch the center of mass, it follows a parabola, right? We've also done this with an explosion, right? Here's a firework. We did one with a shell that broke into two pieces. But at any point along this, right, even though all the pieces move off in different directions, the center of mass still keeps following this trajectory, right? These particles in the front are now moving faster. These particles in the back are moving more slowly, but the whole center of mass is still the external force on the whole thing is still just the force of gravity. So it's still going to follow projectile motion, right? So if we go back to this example of the pulley, what is the acceleration of the center of mass for the Atwood machine? Well, the net force on each of these objects externally is just going to be the difference between the two weights, because the tension is an internal force. And that's actually how we found the acceleration before, right? We took the difference of the forces on the system and we divided it by the total mass. So Newton's laws for a system of particles then says the acceleration of the center of mass is the net force external to the system divided by the total mass. And if net external force is zero, then the acceleration of the center of mass is zero. Nothing is new there. That's just a restatement of Newton's first and second laws. But just being specific that we're not talking about an individual object, that's all connected. We're talking about a bunch of particles. If no net external forces act on a system, then V, the velocity of the center of mass, will stay constant, which means it could stay at rest, or if it was already moving, it will keep going. So here's an interesting result. A cannon is rigidly mounted to the floor of a sealed railroad car at rest on a frictionless track. The cannon fires cannonballs to the right. The balls hit the wall and land on the floor. So they go across, hit, and fall down. So there's lots going on here, but where's the railroad car after the balls have all been fired? Well, if you think about what's happening here, there's kind of a couple ways to consider this. You can think about the fact that at the beginning, this pile of cannonballs is right next to the cannon. And at the end, it's over on the other side of the car. And in order for that to happen, right, there's no net external force on this system. So if the mass moves around, right, the inside, the center of mass of the whole railroad car, cannonball thing should stay in the exact same spot. So when the balls hit the wall, they apply a force on the car, and the car applies a force on the ball, right? What happens to the train when the ball is fired? Well, at first the ball goes to the right, the train moves a little bit to the left. When the ball and the train hit each other, they collide and fall down, and then it stops it. So every time you fire it, the train moves a little bit to the left. So how could we figure out the total displacement of the train? Well, if the net external force is zero, the acceleration of the center of mass is zero. That means we know that the center of mass stays in the same place. And if all of the cannonballs move to the far side, then the center of mass is in the same place. But since the mass has been redistributed, the whole thing has to be moved. Even while the cannons fire and the balls fly through the air, the center of mass must stay in the same place because there's no net external force. A slightly more small scale example, right? 20 kilogram child sits on a 100 kilogram raft that is 4 meters long. If the child walks to the other side of the raft, how far does the raft move? How far does he move? Well, the center of mass of this system, because there's no net external force on it, has to stay in the same place. And initially, the center of mass can be calculated to be at 1.67 meters, which means the center of mass still needs to be at 1.67 meters, but the child has moved. And so in order for the center of mass to be there, right, it has to be 1.67 meters from the child. So the entire system shifts. And that ends up being about 66 centimeters of movement. This is another great example, and I'm not going to go through all the details. This is on page 35 in your packet, which you might want to look at. We'll talk about it in class. But we have a frog that leaps from one end of this board to the other. It's all frictionless, so it's free to slide. So it's basically like the child walking across. So the question is, what's the minimum takeoff speed that allows the frog to do the trick? And so you have to think a little bit about this. How far is the frog moving? How is the frog jumping? An interesting problem to consider. How would you go about solving this? There are a couple different ways. Reference frame switching might be something you would consider. And again, we'll talk about it in class together. All right, so the big idea here is that the system of particles can be treated as a single object using our understanding of momentum, impulse, when is momentum conserved, how do impulses behave, and that can allow us to do a lot of things that we might otherwise before have thought were too complicated.